Hello students, I am Hemant Kumar Nayak and I will teach chemistry today in organic section, organic chemistry. I will teach you. So now I am sharing my screen to you. And, we start today's class. So for that I am sharing my screen. So let's share. Now you can see organic chemistry, some basic principle and techniques. So, okay, I will annotate. This is organic chemistry part. And first, I will start some basic principles and techniques of organic chemistry. So now, as you have learned that the element carbon has unique property called catenation, due to which it forms covalent bonds with other carbon atoms. It also forms covalent bonds with atoms of other elements like hydrogen, oxygen, nitrogen, sulfur, phosphorus, and halogens. The resulting compounds are studied under a separate branch of chemistry called organic chemistry. So organic chemistry is basically for carbon and its a compound. Okay, so now general introduction. Organic compounds are vital for sustaining life on Earth and include complex molecules like genetic information bearing deoxyribonucleic acid (DNA) and proteins that constitute essential compounds of our blood, muscles, and the skin. Organic chemicals appear in materials like clothing, fuels, polymers, dyes, and medicines. These are the some of the important areas of application of this compound. Okay, so we can see organic compound like infused polymers, dyes, and medicines. The science of organic chemistry is about 200 years old. Around the year 1780, chemists began to distinguish between organic compounds obtained from plants and animals and inorganic compounds prepared from mineral sources. Urea Uh, this notion was rejected in 1829. This is not important. So first we'll talk about organic compound like urea, and F. Fowler synthesized an organic compound urea from an inorganic compound ammonium cyanide. So, ammonium cyanide is raw material to produce urea, and ammonium cyanide is inorganic compound, and in presence of heat we can produce urea. So this is the important. The pioneer synthesis of acetic acid by Kolbe 1845 and that of methane by Berthelot 1856 showed conclusively that organic compound could be synthesized from organic sources in a laboratory. Now, tetravalence of carbon, shapes of organic compound. So as you know, carbon is a tetravalence carbon and the shape of carbon compound. The knowledge of fundamental concept of molecular structure helps in understanding and predicting the properties of organic compound. You have already learned theories of valency and molecular structure in Unit 4. So this part you have learned. So we are going to study about organic chemistry. So we'll talk about carbon compound. So you and you already know that tetravalence of carbon. So carbon has tetravalency, and the formation of covalent bond by it are explained in terms of electronic configuration and the hybridization of s and p orbital. It may be recalled that the formation and the shapes of molecules like methane, CH4, ethane, C2H4, ethane, C2H2 are explained in terms of use of uh, sp3, sp2, and the sp hybrid orbitals by carbon atom in the respective molecules. So hybridization influences the bond length and the bond enthalpy strength in organic compounds. The sp hybrid orbital contains more s character and hence it is closer to its nucleus and forms shorter and a stronger bond than the sp3 hybrid orbital. The sp2 hybrid orbital is intermediate in s character between sp and sp3. Hence, the length and the enthalpy of the bonds it forms are also intermediate between them. The change in hybridization affects the electronegativity of carbon. The greater the s character of the hybrid orbitals, the greater is the electronegativity. Thus, a carbon atom having an sp hybrid orbital with 50% s character is more electronegative than that possessing sp2 or sp3 hybridized orbitals. This relative electronegativity is reflected in several physical and chemical properties of the molecules concerned about which you will learn in this later. Some characteristic features of pi bonds. So pi bonds and sigma bonds is also there. In a pi bond formation, parallel orientation of the two p orbitals on adjacent atoms necessary for proper sideways overlap. Thus, H2C double bond CH2 molecules, these molecules, all the atoms must be in the same plane. The p orbitals are mutually parallel and both the p orbitals are perpendicular to the plane of the molecule. Rotation of one CH2 fragment with respect to other interpairs with maximum overlap of p orbitals and therefore such rotation about carbon-carbon double bond C double bond C is restricted. The electron charge cloud of the pi bond is located above and below the plane of bonding atom. This results in the electron being easily available to the attacking region. In general, pi bonds provide the most reactive centers in the molecules containing multiple bonds. How many sigma and pi bonds are present in each of the following molecules? So this is the questions we have to answer. First is this, and second is this. So for counting sigma bond and pi bond, you have to make the structure first. So every single bond has one sigma bond, and every pi bond have one sigma and one pi, and the triple bond have two sigma and two pi and one sigma. So for carbon there are 4 sigma bond, and carbon hydrogen 6 sigma bond, and carbon double bond 1 sigma bond. In double bond 1 pi bond is there, and in triple bond 2 pi is there, and 2 pi bond is there. This is the thing, and for this compound, let's make draw. So this is the compound. So C here, this will be written as like this. C and H here. Again C, and 3 hydrogen are attached to it. So for counting sigma and pi bond, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 sigma bonds are there, and for pi bond, we have 1 pi bond, 2 pi bond. So in this compound, we can see that there are 9 sigma bonds and 2 pi bond. Like that, we have to calculate number of sigma and pi bond. So what is the type of hybridization of each carbon in the following compound? So this is the thing. So here CH3Cl. So first we have to draw structure. So here Cl and the 3 hydrogen molecule. So here 1, 2, 3, 4 sigma bond means sp3. So if 4 sigma bond are there, then sp. Like similarly, there are different ways. sp2 hybridized carbon triangular planar. sp3 hybridized carbon tetrahedral. Its shape is tetrahedral. And if sp hybridized carbon is there, then linear. So you have to remember is shape also. If sp2 hybridization is there, so planar structure will be there, and sp3 tetrahedral shape will be there. And for sp hybridized carbon linear. These are the things for counting sigma and pi bond or any compound. Okay. Now I will teach about structural representation of organic compound. Complete condense and the bond line structural formulas. Structure of organic compound are represented in several ways. The Lewis structure or dot structure, dash structure, condense structure, and the bond line structure formulas are some of the specific types. The Lewis structure, however, can be simplified by representing the two electron covalent bond by a dash. Such a structure formula focuses on the electrons involved in bond formation. A single class represents a single bond, double dash is used for double bond, and triple dash represent triple bond. Lone pair electron on heteroatoms, example oxygen, nitrogen, sulfur, halogen, it is may or not be shown. Thus, ethane C2H6, ethene C2H4, ethine C2H2, and methanol CH3OH can be represented by following structural formula. Such structural representations are called complete structural formula. Like ethane, we can this is ethane formula for ethane, structural formula for ethane, and this is for ethene. Like that, we have formula for ethine and for methanol. Like that, these structural formulas can be further abbreviated by omitting some or all of the dashes representing covalent bonds and by indicating the number of identical groups attached to an atom by subscript. The resulting expression of the compound is called a condensed structural formula. Thus, ethane, ethene, ethine, and methanol can be written as ethane is written as CH3CH3 and ethane is H2C CH2, ethine HCCH CH3OH. Like that, we can represent different compound with the structural formula. So this is the thing. There are different ways to represent. In cyclic compound, the bond line formulas may be given as follows: CH2 if we have CH2 for this structure, then we can represent like that. That is cyclopropane, and so these are the representation for different compound. How to represent like chlorocyclohexane, we can write like that, and these are the some problem. Expand each of the following condensed formula into their complete structural formula. So we have CH3, CH2, CH, CH2, so we have to draw like that. So it's condensed formula is into their complete structural. This is complete structural formula for problem given in A section, and in B, this is the structural formula. And next problem says for each of the following compound, write a condensed formula and also their bond line formula. So bond line and condensed formula, we can write condensed formula is like that, and bond line formula which we can represent like that. So this is just representation of different structures like structural condense and a bond line. So this is the bond line. This type of this is structural, and this one is condensed. Similarly, different type of compound we can represent in different form, and some models are there like a molecular model. Molecular model are physical devices that are used for better visualization and perceptions of three-dimensional shapes of organic molecules. These are made of wood, plastic, or metal and are commercially available. Commonly, three types of molecular models are used: framework model, ball and stick model, space filling model. In the framework model, only the bond connecting the atoms of a molecule and not the atoms themselves are shown. This model emphasizes the patterns pattern of bond of molecule while ignoring the size of atom. In the ball and the stick model, both the atoms and the bonds are shown. Balls represent atoms and the stick denotes a bond. Compound containing C double bond C, example ethene, can best be represented by using springs in place of sticks. These models are referred to as ball and spring model. The space filling model emphasizes the relative size of each atom based on the van der Waals radius. Bonds are not shown in this model. It conveys the volume occupied by each atom in the molecule. In addition to these models, computer graphics can also be used for molecular modeling. So these are some models like framework model, you can see, and ball and stick model, it look like that. These are the ball, and in between balls there are sticks, like that. And the space filling model is like look like that. So these are the different models. And now I'm going to classify of organic compound. Different classifications are there. The existing large number of organic compounds and their ever increasing numbers has made it necessary to classify them on the basis of their structure. Organic compounds are broadly classified as follows. So there are different organic compounds. First, acyclic or open chain compound, and then cyclic or closed chain ring compounds. Okay, so first we are divided into, and so closed or cyclic compound or ring compound is divided into two parts. First is homocyclic or carbocyclic compound, and second is heterocyclic compound. Okay, so carbocyclic compound is divided into two parts: alicyclic compound and aromatic compound. Aromatic compound is again classified into two parts: benzoate compound, non-benzoate compound. So these are classification of different organic compounds. So first we are seeing about acyclic or open chain compound. Acyclic or open chain compound. These compounds are also called as aliphatic compound. Okay, so open chain compounds are also called aliphatic compounds and consist of straight or branch chain compound. For example, ethane, CH3CH3, and the isobutane, CH3CH3 isobutane, and acetaldehyde, CH3COOH, acetic acid, CH3COOH. Okay, so now the second thing is alicyclic or closed chain or ring compound. Alicyclic, aliphatic cycle compound contain carbon atom join in the form of ring. Aliphatic ring. Homocyclic, sometimes other or atoms other than carbon are also present in the ring. Heterocyclic, some examples of this type compounds are cyclopropane, cyclohexane, and cyclohexane tetrahydrofuran. This is a structure for tetrahydrofuran. These exhibit some of the properties similar to those of aliphatic compound. Aromatic compound. Now aromatic compound. Aromatic compounds are a special type of compound. We will learn about these compounds in detail in Unit 13. These include benzene and other related ring compounds. Benzenoid, like alicyclic compounds, aromatic compounds may also have hetero atom in the ring. Such compounds are called heterocyclic aromatic compounds. Some of the examples of various types of aromatic compounds are benzoate aromatic compound, like benzene structure is this, aniline, see that naphthalene, naphthalene is this, non-benzoate compound, propylene. This is a structure for propylene. Heterocyclic aromatic compound. In this different atoms which are oxygen in this sulfur, in this nitrogen. So this is pyridine, thiophene, and this is furan. Organic compounds can also be classified on the basis of functional group into families or homologous series. Functional group. The functional group may be defined as an atom or group of atoms joined in a specific manner, which is responsible for the characteristic chemical properties of the organic compound. The examples are hydroxyl group, OH, aldehyde group, CHO, and carboxylic group, COH. Homologous series. A group or a series of organic compounds, each containing a characteristic functional group, forms a homologous series, and the members of the series are called homologous. The members of a homologous series can be represented by general molecular formula, and the successive members differ from each other in molecular formula by a CH2 unit. These are number of homologous series of organic compounds. Some of these are alkanes, alkenes, alkynes, haloalkanes, alkenols, alkenones, alkenoic acid, amine. Nomenclature of organic compound. Nomenclature of organic compound. Organic chemistry deals with millions of compounds in order to clearly identify them. A systematic method of naming has been developed and is known as IUPAC, International Union of Pure and Applied Chemistry System of Nomenclature. In this systematic nomenclature, the names are correlated with the structure such as that the reader or listener can deduce the structure from the name. Before the IUPAC system of nomenclature, however, organic compounds were assigned names based on their origin or certain properties. For instance, the citric acid is named as so because it is found in citrus fruits, and the acid found in red and is named formic acid since the Latin word for ant is formica. These names are traditional and are considered as trivial or common names. Some common names are followed even today. For example, Buckminster Fuller is a common name given to the newly discovered C60 cluster, a form of carbon, noting its structure similarly to the geodesic domes popularized by the famous architect or Buckminster Fuller. Common names are useful and in many cases indispensable, particularly when the alternative systematic name are lengthy and complicated. Common names of some organic compounds are given in table 12.1. Common or trivial names of some organic compounds, like compound common name CH4, we can say methane, H3C, CH2, CH2, CH3, and butane, and CH3C2, CH3, isobutane, CH3, 4C, biopentane, CH3, CH2, CH2OH, and propyl alcohol. Okay. Okay, so these are the different compound, and these are this name, like SCHO, formaldehyde, and CH3 2CO acetone, chloroform, CSCS3, chloroform, CH3COH, acetic acid, CCS6 benzene, CCS5OCH3, anisole, CCS5NH2, aniline. These are the common names. The IUPAC system of nomenclature. A systematic name of an organic compound is generally derived by identifying the parent hydrocarbon and the functional group attached to it. See the example given below. Functional group is a OH, it's hydroxyl group, and BR functional group. This is branch, CH3. Parent chain. This is parent chain. So, like that. By further using prefixes and suffixes, the parent name can be modified to obtain the actual name. Compound containing carbon and hydrogen only are called hydrocarbons. Hydrocarbon system saturated if it contains only carbon single bond. The IUPAC name for a homologous series of such a compound is alkane. Paraffin, Latin, little affinity, was the earlier name given to these. Unsaturated hydrocarbons are those which contain at least one carbon double or triple. Okay, so unsaturated hydrocarbons are those which contain at least one carbon double or triple bond. And next is IUPAC nomenclature of alkanes. So straight chain hydrocarbon. The names of such compound are based on their chain structure and end with suffix n and carry a prefix indicating the number of carbon atoms present in the chain except from CH4 to C4H10. The prefixes are derived from trivial names. The IUPAC name of such a straight carbon, some straight carbon chain saturated hydrocarbons are given 12.2. The alkanes in table 12.2 differ from each other by merely the number of CH2 groups in the chain. They are homologous of alkane series. IUPAC name of some unbranched saturated hydrocarbon like methane CH4, ethane C2H6, propane C3H8, butane C4H10, pentane C5H12, hexane H14, like that. Different types name of the branch chain hydrocarbon. In a branch chain compound, small chain of carbon atoms are attached at one or more carbon atom of the parent chain. The small carbon chain branches are called alkyl group. For example, CH3, CH2, CH3. This is alkyl group we are talking about. And in order to name such compound, the name of alkyl group are prefixed to the name of parent alkane. An alkyl group is derived from a saturated hydrocarbon by removing the hydrogen atom from carbon. Thus, CH4 becomes CH3 and is called methyl group. Okay, this is the way. And alkyl group is named by substituting YL or ANE, the corresponding alkane. Some alkyl group are listed in table 12.3. CH4 methane, if you remove one hydrogen, then it will become CH3 and we call methyl. Like that, ethane we call ethyl and decane methyl. Abbreviations are used for some alkyl group. For example, methyl is abbreviated as Me, ethyl as Et, propyl as PR, and butyl as Bu. The alkyl groups can be branched. Also, the propyl and butyl group can have branch structure as shown below. Isopropyl, secondary butyl, isobutyl, third butyl, neopentyl. Common branch group have specific trivial name. For example, the propyl group can either be N-propyl group or isopropyl group. The branch butyl groups are called secondary butyl, isobutyl, and third butyl group. We also encounter the structure in CH2C, CH2C, which is called neopentyl group. Nomenclature of branch chain alkane. We encounter a number of branch chain alkane. The rules of naming them are given below. First of all, the longest carbon chain in the molecule is identified. In the example given below, the longest chain has 9 carbon and it is considered as the parent or root chain. Selection of parent chain as shown in 2 is not corrected because it has only 8 carbon. First, we have to see longest chain in the structure. So this is longest chain 1, 2, 3, 4, 5, 6, 7, 8, 9 carbon is there. Okay, so if you count like 1, 2, 3, 4, 5, 6, 7, 8, so it is 8. So we choose first because it is 9. And second thing is the carbon atom of the parent chain are numbered to identify the parent alkane and to locate the position of the carbon atom at which branching takes place due to the substitution of alkyl group in the place of hydrogen atom. The numbering is done in such a way that the branch carbon atom gets the lowest possible number. Thus, the numbering in the above example should be from left to right, branching at carbon atom 2 and 6. And not from right to left in number 4 and 8 to the carbon atom. At which branches are attached? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so 1, 2, 3, 4. The name of alkyl group attached as a branch are then prefixed to the name of the parent alkane and the position of the substituents is indicated by the appropriate number. If different alkyl groups are present, they are listed in alphabetical order. The name for the compound shown above is 6-ethyl 2-methyl known as 6-methyl 6-methyl 2-methyl 2-methyl alphabetical order. So 6-ethyl, 2-methyl, no name. Okay, so its name is like that, separated from the group by hyphen, and there is no break between methyl and the no name. Hyphen, we have to separate by hyphen. This is important. The fourth point is if two or more identical substituent groups are present, then the number are separated by comma. The names of identical substituent are not repeated. Instead, prefixes such as di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, etc. are used by writing the name of the substituent in alphabetical order. These prefixes, however, are not considered, thus the following compounds are named as 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So 2,4-dimethyl pentane, 2,4-dimethyl pentane. And this is 2,2,4-2,2,4-trimethyl pentane. And in third one is you can write 3-ethyl 4,4-dimethyl pentane. If the two substituents are found in equivalent position, the lower number is given to the one coming first in the alphabetical listening. Thus, the following compound is 3-ethyl 6-methyl, 3-ethyl 6-methyl, methyl octane, and not 6-ethyl 3-methyl octane. Then compound is 3-ethyl 6-methyl octane. The branch alkyl group can be named by following the above mentioned procedure. However, the carbon atom of the branch that attaches to the root alkane is numbered 1 as exemplified below. 1,3-dimethyl-butyl. Carbon atom of the branch that attaches to the root alkane is numbered 1. Okay. 1, 2, 3. Okay. 1,3-dimethyl-butyl. These are the rules for nomenclature of organic compound. The name of such branch chain alkyl group is placed in parentheses while naming the compound. While writing the trivial names of the chain in alphabetical order, the prefixes iso and neo are considered to be the part of the fundamental name of alkyl group. The prefixes sec and tut are not considered to be the part of the fundamental name. The use of iso and related common prefixes for naming alkyl group is also allowed by the IUPAC nomenclature as long as these are not further substituted in multi-substitute compound. The following rule may also be remembered. The first is if there happens to be two chains of equal size, then that chain is to be selected which contains more number of side chains. Second is after selection of the chain, numbering is to be done from the end closer to the substituent. For example, is first we count 1, 2, 3, 4, 5, 10. Okay, so 1, 2, 3, 4 are together. So 5, in 5, 2-ethyl butyl, and the 3,3-dimethyl, 3,3-dimethyl decade, and not 5,2,2-dimethyl, 3-ethyl decade. Like that 5 secondary butyl, 5 secondary butyl, 4 isopropyl, 4 isopropyl decade, and the 5 2,2-dimethyl, 5 2,2-dimethyl propyl, like that we have to name the compound. So for cyclic compound, a saturated monocyclic compound is named by prefixing cyclo to the corresponding state chain alkane. If side chains are present, then the rules given above are applied. Names of some cyclic compound are given below. Cyclopentane, alphabetical order of numbering 1, 2, 3, 1-methyl, 3-propyl cyclohexane. So more branch carbon gets lower number. 1, 2, 3. 3-ethyl 1,1 dimethyl cyclohexane, not 1-ethyl T3 dimethyl. More branch carbon gets lower number. More branch carbon gets lower number. 3-ethyl 1,1 dimethyl cyclohexane. Structure and IUPAC name of some hydrocarbons are given below. Explain why the names given in the parentheses are incorrect. CH3CH, this is the problem. First, 2,5,6 trimethyl. This is I'm talking 2,5,6 trimethyl octane. It is not 3,4,7 trimethyl octane. So 2,5,6 trimethyl. 1, 2, 3, 4, 5, 6, 7, 8. So 2,5,6 trimethyl octane, not 3,4,7 trimethyl. Lowest locant number 2,5,6 is 4, then 3,5,7, and for B, 3-ethyl, 5-methyl, and not 5-ethyl. So substituent are in plain position. Lower number is given to the one that comes first in the name according to alphabetical order. So alphabetical order, lower name is ethyl to 3-ethyl. So that's why 3-ethyl, 5-methyl, and then we call. Nomenclature of organic compound having functional group. A functional group, as defined earlier, is an atom or group of atoms bonded together in a unique manner, which is usually the site of chemical reactivity in an organic molecule. Compounds having the same functional group undergo similar reaction. For example, CH3OH, CH3CH2OH, CH3CH2CHOH, all having OH functional group, liberate hydrogen on reaction with the sodium metal. The presence of fundamental group enables systematization of organic compound into different classes. Example of some functional group with their prefixes and suffixes, along with some examples of organic compound processing. These are given in table 12.4. First of all, the functional group present in the molecule is identified, which determines the choice of appropriate suffix. The longest chain of carbon atom containing the functional group is numbered in such a way that the functional group is attached at the carbon atom possessing lowest possible number in the chain. By using the suffix as given in table 12.4, the name of compound is read. In the case of polyfunctional compound, one of the functional group is chosen as the principal functional group and the compound is then named on that basis. The remaining functional group, which are subordinate functional group, are named as substituent using the appropriate prefixes. The choice of principal functional group is made on the basis of order of preference. The order of decreasing priority for some functional group is first is COA, NSO3A, COR, R alkyl group, COCl, CONH2, CNSC, so COOH, NH2, C1C, C1C. The R C6H5 hydrogen F, ClBri, NO2, alkoxy, GCRL, which prefix substituent. Thus, a compound containing both an alcohol and a keto group is named as hydroxyalkanone, since the keto group is preferred to the hydroxyl group. For example, HOCH2CH2CH3CH2COCH3 will be named as 7-hydroxyheptane 2-one and not as 2-oxoheptane 7-all. Similarly, BrCH2CH2 is named as 3-bromo 1-ene and not 1-bromo 2-ene. If more than one functional group of the same type are present, the number is indicated by setting di, tri, etc. before the class. Okay. In such cases, the full name of the parent alkane is written before the class suffix. For example, CH2OH. CH2OH is named as ethane 1,2-diol. However, the ending Ne of the parent alkane is dropped in the case of compound having more than one double or triple bond. For example, CH2 double bond, CH single bond, CH double bond, CH2 is named as buta 1,3-diene. Problem: write the IUPAC name of the compound 1 to 4 from their given structure. The functional group present is an alcohol, OH, hence the suffix is ol. Longest chain containing OH has 8 carbon atoms, hence the corresponding saturated hydrocarbon is octane. So OH is in carbon atom 3. In addition, a methyl group is attached at 6th position. The systematic name of this compound is 6-methyl octane. 6-methyl octane TR. Okay. The second is there. So the functional group present is ketone because C double bond O is the suffix on. Presence of two keto group is indicated by di in suffix become dione. The two keto groups are at carbon 2 and 4. The longest chain contains 6 carbon atoms. Current hydrocarbon is hexane. The systematic name is hexane 2,4-dione. And the third is there. For third, there are two functional groups, namely ketone and carboxylic acid are present. The principal functional group is the carboxylic acid group. In the parent chain will be suffixed with oic acid. Numbering of the chain start from carbon of COH functional group. The keto group in the chain at carbon 5 is indicated by oxo. The longest chain, including indicating the principal functional group, is 6 carbon atoms. Hence, the parent hydrocarbon hexane. The compound is therefore named as 5-oxohexanoic acid. And the fourth compound is written is that the two C double bond C functional group are present at carbon atom 1 and P, while the C double triple bond C functional group is present at carbon 5. These groups are indicated by suffix di and yin, respectively. The longest chain containing the functional group has 6 carbon atom, hence the parent hydrocarbon is hexane. The name of compound therefore is hexa 1,3-di 5-ion. Hexa 1,3-di 5-ion. Problem 12.9. And this is the table, sum of functional group and classes of organic compound. Class of compound alkane, functional group is structure, natrium. IUPAC group suffix N, and example butane, CH2, twice CH3, alkenes, in but 1 in halide, X will be FCl, BRI, hello, alcohols, OH, hydroxy, aldehyde, CH2 forme, or oxo, ketones, oxo, nitric or cyano, ethers, ROR, alkoxy, carboxylic acid, COH, carboxylic acid, carboxylate ion, COA, wet, ester COR, alkoxycarbonyl, wet, acyl halide, COX, halocarbonyl, oil halide, amines, NH2, amino amine, amides, CONH2, CONHR, CONH, NR2, carbo, moil, amide, nitrose, NO2, nitrose. Problem 12.9 says derive the structure of 1,2-chlorohexane, second pent 4-ENO2-ol, 3-nitrous cyclohexane 1-ol, 6-hydroxyethanol. So now name is there and we have to find the structure. Hexane indicates the presence of 6 carbon atom in the chain. Functional group chloro is present at carbon 2. In the structure of the compound is CH3, CH2, CH3. And the second pent indicates that parent hydrocarbon contains 5 carbon atoms. The chains En and all correspond to the functional group 0-1C and OH at the carbon 4 and 2 respectively. The structure is CH2, 1CH, CH2, CH2, CH3. Similarly, we can write the structure. Nomenclature of substituted benzene compound. For IUPAC nomenclature of substituted benzene compound, the substituent is placed as prefix to the word benzene as shown in the following example. However, common names written in bracket below of many substituted benzene compounds are also universally used. These are the benzene compound like toluene, methyl benzene, and anisole, methoxybenzene, aminobenzene, aniline, nitrobenzene, bromobenzene. Benzene is distributed. The position of substituent is defined by numbering the carbon atom of the ring such that the substituents are located at the lowest numbers possible. For example, the compound B is named as 1,3-dibromobenzene, not as 1,5-dibromobenzene. 1,2-dibromobenzene, 1,3-dibromobenzene, 1,4-dibromobenzene. In the trivial system of nomenclature, the term morpho, meta, and para P are used as prefix to indicate the relative positions. 1, 2, 1, 3, and 1, 4 respectively. Thus, the 1, 3 dibromobenzyl B is named as meta-dibromobenzyl. Meta is abbreviated as met M, and the other isomer of dibromobenzyl 1, 2, and 1, 4 are named as R4, or just 4, and para, or just P, dibromobenzyl, respectively. A tri or higher substituted benzene derivative, these prefixes cannot be used, and the compound are named by identifying substituent positions on the ring by following the Lewis-Loken rule. In some cases, common name of benzene derivative is taken as the base compound. The substituent of the base compound is assigned number 1, and then the direction of numbering is chosen such that the next term to substituent gets the lowest number. The substituent appear in the name in alphabetical order. Some examples are given below. Okay, so 1-chloro 2,4-dinitrobenzene, not 4-chloro 1,3-dinitrobenzene. 1-chloro 2,4-dinitrobenzene you can call, and the next is 2-chloro 1-methyl-4-nitrobenzene. 2-chloro 1-methyl, 2-chloro 1-methyl-4-nitrobenzene. And the next is 2-chloro-4-methyl-anisole, 4-ethyl-2-methyl-aniline, 4-ethyl-2-methyl-aniline, 3,4-dimethylphenol. When a benzene ring is attached to an alkane with a functional group, it is considered a substituent. Instead of a parent, the name of our benzene as substituent is phenyl. C6H5 also abbreviated as PA. We write the structural formula of following. So this is a problem. Different carbon skeletons, these are referred to as chain isomer, and phenomena is termed as chain isomerism, for example. Next topic is, which is a very important topic, and which is this isomerism. In the can come from the phenomena of existence of two or more compounds possessing the same molecular formula but different properties is known as isomerism. So this is the important term. Same molecular formula but different properties is known as isomerism. Such compounds are called as isomers. Okay. So we have same molecular formula but different properties. The following flow chart shows different types of isomerism. So first is structural isomerism. Compound having the same molecular formula but different structures, manners in which atoms are linked are classified as structural isomers. Some typical examples of different types of structural isomerism are given below. Okay, so chain isomerism, when two or more compounds have similar molecular formula but different carbon skeleton, these are referred to as chain isomer. The phenomena is termed as chain isomerism. For example, C5H12 represents three compounds: pentane CH3CH2CH2CH2CH3, azopentane CH3CH3CH2CH3, neopentane 2,2-dimethylpropane. And next is position isomerism. When two or more compounds differ in the position of the substituent atom or functional group on the carbon skeleton, they are called position isomer, and this phenomena is termed as position isomerism. For example, the molecular formula C3H8O represents two alcohol, propane 1-ol, CH3CH2CH2OH, CH3CHOH, CH3, propane 2-ol. Okay, so propane 1-ol and propane 2-ol are the position isomerism. Next is functional group isomerism. Two or more compounds having the same molecular formula but different functional groups are called functional isomer, and this phenomena is termed as functional group isomerism. For example, the molecular formula C3H6O represents an aldehyde and a ketone. And the isomerism we can classify it in different types. Okay, so isomerism is the beginning, and the one question definitely come from isomerism sector. This is a structural isomerism. This is stereoisomerism. So in structural isomerism, we talk about chain isomerism. Next is position isomerism and functional group isomerism, and next is metamerism. And in stereoisomerism, geometrical isomerism is there, and optical isomerism is also there. So another example of position isomerism is CH3CO CH3 propanone, CH3CH2H cis-1 propanone. And next category is metamerism. It arises due to different alkyl chain on either side of the functional group in the molecule. For example, C4H10O present methoxypropane, CSO, C3H7, and ethoxy, and C2H5O, C2H5. And now I'm talking about the stereoisomerism. Okay, stereoisomerism. Stereoisomerism. A compound that has the same constituent and sequence of covalent bond but differ in relative position of their atoms or group in space are called stereoisomers. This special type of isomerism is called as stereoisomerism and can be classified as geometrical and optical isomerism. Fundamental concept in organic reaction mechanism. In an organic reaction, the organic molecule also required a substrate react with an appropriate attacking agent and it leads to the formation of one or more intermediate and finally product. The general reaction is depicted as below. Organic molecules, some substrate will be there, attacking reagent will be there, and then intermediates form, and then finally products and some byproduct will also form. Substrate is that reactant which supplies carbon to the new bond, and the other reactant is called reagent. If both the reactants supply carbon to the new bond, the choice is arbitrary, and in that case, the molecule on which attention is focused is called substrate. In such a reaction, a covalent bond between two carbon atoms or a carbon and some other atom is broken, and a new bond is formed. A sequential account of each step describing details of electron movement, energetics during bond cleavage and bond formation, and the rate of transformation of reactant into product kinetics is referred to as reaction mechanism. The knowledge of reaction mechanism helps in understanding the reactivity of organic compound and in planning strategy for their synthesis. In the following sections, we shall learn some of the principles that explain how these reactions take place. Okay, so this is a bit interesting, man. So now I will be teaching about some reactions in the following. Like fission of a covalent bond. A covalent bond can get cleaved either by heterolytic cleavage and or by homolytic cleavage. In heterolytic cleavage, the bond breaks in such a fashion that a shared pair of electrons remains with one of the fragments. After heterolysis, one atom has a sextet electronic structure and a positive charge, and the other a valence octet with at least one lone pair and a negative charge. The heterolytic cleavage of bromomethane will give CH3 and a Br as shown below. H3C Br is giving rise to H3C plus Br minus. A species having a carbon atom possessing sextet of electron and a positive charge is called a carbocation, either called carbonium ion. The CH3 ion is known as methyl cation or methyl carbonium ion. Carbocations are classified as primary, secondary, or tertiary, depending on whether 1, 2, or 3 carbons are directly attached to the positively charged carbon. Some other example of the carbocations are CH3, CH2, ethyl cation, a primary carbocation, CH3 twice CH isopropyl cation, a secondary carbocation, CH3 thrice C terbutyl cation, a tertiary carbocation. Carbocations are highly unstable and reactive species. Alkyl group directly attached to the positively charged carbons stabilize the carbocation due to inductive and hyperconjugation effect, which we will see will be studying in the section 12.7.5 and 12.7.9. The observed order of carbocation stability is CH3 is less than CH3, CH2 is less than CH3, 5CH is less than CH3, 5C. These carbocations have regional planar shape with the positively charged carbon being sp2 hybridized. The shape of CH3 may be considered as being derived from the volume of 3 equivalent sp2 hybridized orbitals. These are the fundamental. We are studying about fundamentals of reaction and how that happens. With one s orbital of each of the 3 hydrogen atom, each bond may be represented as CsP2H1s sigma bond. The remaining carbon orbital is perpendicular to the molecular plane and contains no electron. Shape of methyl cation. The heterolytic cleavage can also give a species in which carbon gets the shared pair of electrons. For example, when group Z attached to the carbon leaves without CH3 group is Z, CH3 plus Z plus electron pair, the methyl anion HCC minus is formed. Such a carbon species carrying a negative charge on carbon atom is called carbanion. Carbanions are also unstable and reactive species. The organic reactions which proceed through heterolytic bond cleavage are called ionic or heteropolar or just polar reaction. In homolytic cleavage, one of the electrons of the shared pair in a covalent bond goes with each of the bonded atom. Thus, in homolytic cleavage, the movement of a single electron takes place instead of an electron pair. The single electron movement is shown by half-headed fish who short arrow. Such cleavage result in the formation of neutral species atom or group which contains an unpaired electron. These species are called free radicals, like carbocations and carboanions. Free radicals are also very reactive. A homolytic cleavage can shown as Rx heat or light, alkyl free radical plus X free radical. Alkyl radicals are classified as primary, secondary, or tertiary. Alkyl radical stability increases as we proceed from primary to tertiary. So methyl free radical is less reactive than methyl free radical, and then isopropyl free radical, and more reactive is third butyl free radical. Organic reactions which proceed by homolytic fission are called free radical, or homopolar or non-polar reactions. And then after 5 minutes, I will be teaching nucleophiles and electrophiles. So now I will talk about nucleophiles and electrophiles. The region that brings an electron pair is called nucleophile, and you pair, that is nucleus seeking, and the reaction is then called nucleophilic. A reagent that takes away an electron pair is called electrophile E+. That is electron seeking. The reaction is called electrophilic. The nucleophile is electron nucleus seeking and electron giving, and electrophile are electron seeking. They want electron. So during a polar organic reaction, a nucleophile attacks an electrophilic center of the substrate, which is that specific atom or part of the electrophile that is electron deficient. Similarly, the electrophiles attack at nucleophilic center, which is the electron-rich center of the substrate. Thus, the electrophiles receive electron pair from nucleophile when the two undergo bonding interaction. A third arrow notation is used to show the movement of an electron pair from the nucleophile to the electrophile. Some examples of nucleophiles are the negatively charged ions with lone pair of electrons, such as hydroxide, HO minus, cyanide, and C minus ions, and the carbon ions are received as neutral molecules such as H2O3 and R2NH. It can also act as nucleophiles due to the presence of lone pair of electrons. Examples of electrophiles include carbocation. Examples of electrophiles include carbocation CH3 plus and neutral molecules having functional group like carbonyl group CO or alkyl halide R3CX, where X is halogen atom. The carbon atom in carbocations has sextet configuration. Hence, it is electron deficient and can receive a pair of electrons from the nucleophile. In neutral molecules such as alkyl halide, due to the polarity of the carbon and halogen CH bond, the partial positive charge is generated on the carbon atom, and hence the carbon atom becomes an electrophilic center at which a nucleophile can attach. Using curved arrow notation, show the formation of reactive intermediates when the following covalent bond undergo hydrolytic cleavage. So these are the problems and solutions. Next is electron movement in organic reaction. The movement of electron in organic reaction can be shown by curved arrow notation. It shows how changes in bonding occur due to electronic redistribution during the reaction. To show the change in position of a pair of electrons, curved arrow start from the point from where an electron pair is shifted and it ends at location to which the pair of electrons may move. Presentation of shifting of electron pair is given below. From pi bond to adjacent bond position, from pi bond to adjacent atom, from atom to adjacent bond position. The movement of single electron is indicated by a single barbed tissue, that is half-headed curve arrow. For example, in transfer of hydroxide ion giving ethanol and in the dissociation of the chloromethane, the movement of electron using curved arrows can be depicted as follows. Electron displacement effect in covalent bond. The electron displacement in an organic molecule may take place either in the ground state under the influence of an atom or a substituent group, or in the presence of an equivalent agent. Next important effect is inductive effect. When a covalent bond is formed between atoms of different electronegativity, the electron density is more towards the more electronegative atom of the bond. Such a shift of electron density results in a polar covalent bond. Bond polarity leads to various electronic effects in organic compound. Let us consider chloroethane CH3CH2Cl, in which the CCl bond is a polar covalent bond. It is polarized in such a way that the carbon 1 gains some positive charge, delta plus, and the chlorine some negative charge, negative. The fractional electronic changes on the two atoms in a polar covalent bond are denoted by symbol delta, and the shift of electron density is shown by an arrow that points from delta plus to delta minus end of the polar bond, CH3CH2Cl. So delta plus delta minus Cl. In turn, carbon 1, which has a developed partial positive charge delta plus, draws some electron density toward it from the adjacent CC bond. Subsequently, some positive charge delta plus develops on carbon 2 also, where delta plus implies relatively smaller positive charge as compared to that on carbon 1. In other words, the polar CCl bond induces polarity in the adjacent bond. Such polarization of the sigma bond caused by the polarization of adjacent sigma bond is referred to as the inductive effect. This effect is caused on to the subsequent bond also, but the effect decreases rapidly as the number of intervening bonds increases and becomes vanishingly small after 3 bonds. The inductive effect is related to the ability of subsequent to either withdraw or donate electron density to the attached carbon atom. Based on this ability, the subsequent can classify it as electron withdrawing or electron donating group, relating to that result. Halogens and many other groups such as nitro NO2, cyano-C, and carboxy COOH, ester COR, redox COA are example OC6H5. etc. are electron withdrawing group. On the other hand, the alkyl group like methyl CH3 and ethyl CH2 are usually considered as electron withdrawing group. Resonance structure. Another important parameter is resonance structure. There are many organic molecules which behavior can be explained by a single layer structure. An example is that of benzene. It's a cyclic structure containing alternating CC single and C double bond. So is inadequate for explaining its character properties. This is structure for benzene. We all know this is the structure for benzene. And as per the above representation, benzene should exhibit 2 different bond lengths due to CC single and C double bond. However, it's determined experimentally benzene has a uniform C bond distance of 139 pm, well intermediate between the CC single 154 picometer and the C double 134 picometer. Thus, the structure of benzene cannot be represented adequately by the above structure. Further, benzene can be represented equally well by the energetically added curve structure 1 and 2. The resonance structure, canonical structure, or contributing structure are hypothetical and immediately do not represent any real molecule. The resonance stabilization energy, the stability by resonance we can say. And now resonance effect. The resonance effect is defined as the polarity produced in the molecule by the interaction of 2 pi bond or between a pi bond and a lone pair of electron present in an adjacent atom. The effect is transmitted through the chain. There are 2 types of resonance or a mesomeric effect designated as R or M effect. Positive resonance effect, a plus R effect. In this effect, the transfer of electron is away from an atom or subsequent group attached to the conjugated system. This electron displacement makes certain position in the molecule of high electron density. This effect is in Lin is shown as, and the negative resonance effect minus R effect. This effect is observed when the transfer of electron is towards the atom or subsequent group attached to the conjugated system. For example, in nitrobenzene, this electron displacement can be reflected. The atoms or subsequent group which represent plus or minus electron displacement effect are as follows: plus R effect, halogen, OHO or OCO or NH2, minus NHR, NR2, NSCO or minus R effect, COA, CCO, double bond or CnNO2. The presence of alternate single and double bond in an open chain or cyclic system is termed as conjugated system. These systems often show abnormal behavior. The example are 1,3-butadiene, aniline, and nitrobenzene. In such a system, the pi electron are delocalized and the system develop polarity. Electromeric effect, E effect. It is a temporary effect. The organic compound having a multiple bond or double or triple bond show this effect in the presence of an attacking region. Only it is defined as the complete transfer of a shared pair of pi electron to one of the atoms joined by multiple bond on the remote of an attacking region. The effect is annualized as soon as the taking region is removed from the domain of the reaction. It is represented by E and the shifting of the electron is shown by a curved arrow. There are two distinct types of electromeric effect: positive electromeric effect plus E effect. In this effect, the pi electron of the multiple bond are transferred to that atom to which the region gets attached. For example, here one C plus H attacking region C. Negative electromeric effect minus E effect. In this effect, the pi electron of the multiple bond are transferred to that atom to which the attacking reagent does not get attached. For example, when electric and electromagnetic effect operate in opposite direction, the electromagnetic effect predominate. Hyperconjugation and important. Hyperconjugation is a general stabilizing interaction. It involves the delocalization of sigma electron of CH bond of an alkyl group directly attached to an atom unsaturated system or to an atom with an unshared p orbital. The sigma electron of CH bond of the alkyl group enter into partial conjugation with the attached unsaturated system or with the unshared p orbital. Hyperconjugation is a permanent effect. Okay. So there are types of organic reaction and mechanism. There like organic reaction can be classified into following categories: substitution reaction, addition reaction, elimination reaction, rearrangement reaction. So these are studied in different unit. Method of purification of organic compound. So method of purification of organic compound will be there. The common technique used for purification are as follows: sublimation, crystallization, distillation, differential extraction, and chromatography. Finally, the purity of a compound is ascertained by determining its melting or boiling point. Most of the pure compound have a soft melting point and a boiling point. Okay, so there are different methods like sublimation. You have learned earlier that on heating, some solid substances can from solid to vapor state without passing through liquid state. The purification technique based on the above principle is known as sublimation and is used to separate sublimable compound from non-sublimable impurities. Next is crystallization. This is one of the most commonly used techniques for the purification of solid organic compound. It is based on the difference in the solubilities of the compound and the impurities in a suitable solvent. The impure compound is dissolved in a solvent in which it is sparingly soluble at room temperature but appreciably soluble at higher temperature. The solution is concentrated to get a nearly saturated solution. On cooling the solution, pure compound crystallize out and is removed by filtration. The filtrate mother liquor contains impurities and a small quantity of the compound. If the compound is highly soluble in one solvent and a very little soluble in other solvent, distillation can be satisfactorily carried out in a mixture of the solvent. Impurities which impart color to the solution are removed by absorbing or activated charcoal. Repeated crystallization becomes necessary for the purification of a compound containing impurities of comparable solubility. The next term is distillation. This important method is used to separate volatile liquid from non-volatile impurities. And the liquid having sufficient difference in their boiling point, liquid having different boiling point, vaporize at different temperature. The vapor are cooled and the liquids so form are collected separately. There are different types of distillation like frictionless distillation. is there, steam distillation is there, differential extraction. When an organic compound is present in an aqueous medium, it is separated by shaking it with an organic solvent in which it is more valuable than water. The organic solvent and the aqueous solution should be miscible with each other so that they form two distinct layers which can be separated by separate funnels. The organic solvent is later removed by distillation or by evaporation to get back the compound. Differential extraction is carried out in separate funnel stone decorating. And then chromatography. Chromatography is an important technique extensively used to separate mixtures into their components, purify components, and also to test the purity of compound. The name chromatography is based on the Greek word chroma for color, since the method was first used for the separation of colored substances found in the plant. In this technique, the mixture of substances is applied into a stationary phase, which may be solid or a pure solvent. A mixture of solvent or gas is allowed to move slowly over the stationary phase. Component of the mixture get gradually separated from one another. The moving phase is called the mobile phase. Based on the principle involved, chromatography is classified into different categories. Two of these are adsorption chromatography and partition chromatography. So these are the things. And next is detection of other elements. Qualitative analysis of organic compound. Qualitative analysis of organic. The element present in the organic compound are carbon and hydrogen. In addition to this, they may also contain oxygen, nitrogen, sulfur, halogen, and phosphorus. Detection of carbon and hydrogen. So for carbon and hydrogen are detected by heating the compound with copper 2 oxide. Copper present in the compound is oxidized to carbon dioxide tested with lime water. It develops turbidity, and hydrogen to water tested with anhydrous copper sulfate, it turns blue. So, see, detection of other elements, nitrogen, sulfur, halogen, and phosphorus present in organic compounds are detected by Lissagnet. The element present in the compound are converted from covalent form into the ionic form by fusing the compound with sodium metal. Following reaction takes place. Test for nitrogen. The sodium poison extract is boiled with iron 2 sulfate and then acidified with concentrated sulfuric acid. The formation of Prussian blue color confirms the presence of nitrogen. Sodium cyanide first reacts with iron 2 sulfate and forms sodium cyanoferrate. On heating with concentrated sulfuric acid, some iron 2 ions are oxidized to iron 3 ions which react with sodium hexacyanoferrate to produce iron 3, hexacyanoferrate to ferriferrocyanide, which is Prussian blue in color. And the test for sulfur, the sodium fusion extract is acidified with acetic acid and lead acid is added to it. A black precipitate of lead sulfide indicate the presence of sulfur. And similarly, test for halogen, the sodium fusion extract is acidified with nitric acid and then treated with the silver nitrate. A white precipitate soluble in ammonium hydroxide shows the presence of chlorine. The yellowish precipitate sparingly soluble in ammonium hydroxide shows the presence of bromine, and the yellow precipitate insoluble in ammonium hydroxide shows the presence of iodine. Test for phosphorus. The compound is heated with an oxidizing agent, sodium peroxide. The phosphorus present in the compound is oxidized to phosphate. The solution is boiled with nitric acid and then treated with ammonium molybdate. A yellow color or precipitate indicate the presence of phosphorus. So this is the reaction. And then quantitative analysis. The percentage composition of element present in an organic compound is determined by the method based on the following principles. Carbon and hydrogen. Both carbon and hydrogen are estimated in one experiment. The known mass of an organic compound is burned in the presence of excess of oxygen and copper 2 oxide. Carbon and hydrogen in the compound are oxidized to carbon dioxide and water respectively. CXHY plus X plus Y by 4 by 2, X CO2 plus Y by 2 H2O. The mass of water produced is determined by passing the mixture through a weight U2 containing an anhydrous calcium chloride. Carbon dioxide is absorbed in another U2 containing concentrated solution of potassium hydroxide. These tubes are connected in series, figure 12.1 for the The increase in mass of calcium chloride and potassium hydroxide gives the amounts of water and the carbon dioxide from which the percentage of carbon and hydrogen are calculated. Let the mass of organic compound be m from mass of water and the carbon dioxide produced be m1 and m2 respectively. Percentage of carbon is calculated 12 into m2 into 100 divided by 12 into m. Percentage of hydrogen calculated 2 into m1 into 100 divided by 12 into m. Like that, for nitrogen, there are two methods for estimation of nitrogen: Dumas method and the Geldahl method. Dumas method, the nitrogen containing organic compound when heated with copper oxide in an atmosphere of carbon dioxide will free nitrogen in addition to carbon dioxide and water. This is the formula for Dumas method. And for Geldahl method, the compound containing nitrogen is heated with concentrated sulfuric acid. Nitrogen in the compound gets converted to ammonium sulfate. The resulting acid mixture is then heated with excess of sodium hydroxide. The liberated ammonia gas is absorbed in an excess of a standard solution of sulfuric acid. The amount of ammonia produced is determined by estimating the amount of sulfuric acid consumed in the it is done by estimating unreacted sulfuric acid left after the absorption of ammonia by titrating it with the standard Kali solution. The difference between the initial amount of acid taken and that left after the gives the amount of acid taken. With organic compound plus H2SO4 gives rise to NH4 2SO4 and then again pass to NaOH. Then you can get Na2SO4 plus 2NH3 plus 2H2O. 2NH3 plus H2SO4 again reacts and take, and then we can get NH4 2SO4. Let the mass of organic compound taken m gram, volume of H2SO4 of molarity m taken V ml. Volume of NH4 of molarity m used for titration of excess of H2SO4 is V1 ml. V1 ml of NaOH of molarity m is equal to V1 by 2 ml of H2SO4 of molarity m. Volume of H2SO4 of molarity m and used is equal to V minus V by 1 by 2 ml. V minus V1 by 2 ml of H2SO4 of molarity m is equal to 2 into V minus V1 by 2 ml of NH3 solution of molarity m. 1000 ml of 1 molar NH3 solution contains 17 gram NH3 or 14 gram nitrogen. 2 into V minus V1 by 2 ml of NH3 solution of molarity m contains 14 into m into 2 into V minus V1 by 2 divided by 1000 gram. Percentage of nitrogen is calculated as 14 into m into 2 into V minus V1 by 2 into 100 by m divided by 1000, and which is equal to 1.4 into m into 2 into 1 V minus V1 by 2 divided by m. Geldahl method is not applicable to compound containing nitrogen in nitro and azo group, and nitrogen present in the ring example leading as nitrogen. This compound does not change into ammonium sulfate under this condition. And similarly for sulfur also you can calculate a known mass of an organic compound is heated in carriers tube with sodium peroxide or cubic nitric acid. Sulfur present in the compound is oxidized to sulfuric acid. It is precipitated as barium sulfate by adding excess of barium chloride solution in water. The precipitate is filtered oxide and weight. The percentage of the sulfur can be calculated from the mass barium sulfate. Okay. And now for phosphorus. Phosphorus, a known mass of an organic compound is heated with a fluoronic nitric acid, whereupon phosphorus present in the compound is oxidized to phosphoric acid. It is precipitated as ammonium phosphomolybdate and H4 3PO4 12MOO3 by adding ammonia and ammonium molybdate. Alternatively, phosphoric acid may be precipitated as MgNH4PO4 by adding magnesium mixture which is ignition yield Mg2P2O7. So these are the methods to know qualitative and quantitative analysis of different compound other than carbon and hydrogen. And for oxygen, the percentage of oxygen in an organic compound is usually found by difference between the total percentage composition 100 and the sum of the percentage of all other elements. However, oxygen can also be estimated directly as follows. A definite mass of an organic compound is decomposed by heating in a stream of hydrogen gas. A mixture of gaseous product containing oxygen is passed through a red hot coke when all the oxygen is converted to carbon monoxide. This mixture is passed through warm and iodine carbon dioxide to pipe when carbon monoxide is oxidized to carbon dioxide producing iodine. Compound is in presence of heat goes to O2 plus other gaseous product and 2 carbon plus O2 at 1373 Kelvin give rise to 2CO. And again, I2O5 plus 5CO give rise to I2 plus 5CO2. The percentage of oxygen can be derived from the amount of carbon dioxide or iodine produced. Here the mass of organic is m gram compound taken. Mass of the carbon dioxide m1 gram. 44 gram of carbon dioxide is equal to 32 gram of oxygen. M1 gram of carbon dioxide contains 32 into m1 divided by 42 gram of oxygen. Percentage of oxygen is calculated 32 into m1 into 100 divided by 44 into m percentage. Presently, the estimation of element in an organic compound is carried out by using macro quantities of substances and automatic experimental techniques. The elements carbon, hydrogen, and nitrogen present in a compound are determined by an apparatus known as CH elemental analyzer. The analyzer substance 1-3 milligram and displays the values on a screen within a short time. Of detailed discussion of such method beyond the scope of this. Okay, so these are the summary. So in this chapter, we basically learned about IUPAC naming and the different types of compound and its classification. Then isomerism, different types of isomerism is there, and then reaction, how reaction occur, different types of reactions, and some effect like different types of effect are there, the numeric effect and the Q effect, hyperconjugation, effect, carbocation, carbo. Anion nucleophile profiles, and after that estimation of organic compound like different elements and qualitative and quantitative. In qualitative short and in quantitative different like carbon, nitrogen, sulfur, phosphorus, oxygen. So this is the thing, and now I am stopping here. Okay. So I'm stopping here. Now I'm stopping recording. So thank you guys for being there, and hope you enjoyed my session. And similarly, I've been practicing, and I will teach you guys. So let's stop here, and see you soon to do for next lecture. So thank you guys for being here.